Hi, hello, and welcome to today's webinar. We're going to be talking about concrete construction delays with AI, how to automate scheduling for success. So we are about to start. Uh, just wait for a minute. Okay, so we're ready to go. So my name is Pablo Derendinger. I'm the CTO at Evers. This is an explanation for people in a hurry. So this is the too long didn't read. We want to use Microsoft Project or Primavera files schedules, scrap them, and use them to predict potential delays in a new project. We are going to analyze the dates, the task types, the resources, weather conditions, any other data that is available in order to do that. So what to expect from this talk? I will show you the full package. Everything will be on the table. We're gonna talk about how to cycle through the data collection, data validation, how to do the training, and an idea of how to implement this with your own data. So we are Evers. This is the company. This is the team working with me. We are an international company. We have a base in Miami, Florida. The company is we have 30 employees. Mainly our projects are in the USA. We have projects in Europe, Latin America, and Australia. Our main markets are digital construction and design automation. So let's jump to the topic. Here we have Tom Cruise in the iconic movie Minority Report, where he was able to predict future crimes. And I'm using this as a starter to this question. Can we know the future using AI? All these breakthroughs that we are seeing every day on AI, can they help us to actually predict and know the future? So the short answer is no, they can't. They can't. There is no enough information. There is no way. There are certain things that are falling to the realm of chaos that we cannot predict. But we can use historical data to estimate the likelihood of an event to occur, which means that how's the possibility of something that happened in the past happen again, given these certain circumstances being repeated. So today I'm going to show you our journey from an idea to a product, where we use the schedules, as we previously mentioned, to predict the delays in construction. This is the index for those of you that are still in a hurry. We're going to talk about understanding the construction delays, basics of predictive analysis, machine learning applied to this scheduling, how to integrate the analytics into the project management, and finally, some recommendations and considerations for you to have in mind. So be aware, we are going to show a little bit of data science jargon, some technicalities. I'm going to screen some Python code. And of course, I will have some bad jokes in the middle, so brace yourself, okay? So construction delays and how they affect the industry. If you're here, you're probably related to the industry of construction, so you know what I'm talking about. But let's just put some numbers into this. So according to this survey in the UK, 80% of projects are unnecessarily delayed by some reason. So 80%, that's a great amount. That means a 15% of over the budget new charges that the constructors have to pay at the end of the project. In the UK, there's yearly 1.6 trillion euros being charged by this, okay? If we check into detail of why the delays occur, on the same survey, we can see that yes, we have weather, we have changes on to specs, finance issues, information issues, this famous RFIs, or maybe the resources, but 31% are caused by poor or unrealistic planning. So a big part of the delays are caused by this problem. So on a nutshell, we can say that 80%, we can extrapolate from this, 80% of projects are going to be delayed, uh, mainly by poorly planning, causing a bunch of dollars in charges just to keep it up with this $1.8 trillion around it. So, how we prevent this? The motto here, the thing that you have to have in mind is that you need to prepare for the best. You need to expect for the best, but be prepared for the worst. This is key. So, in with this sentiment, we go to implement predictive analysis to go beyond what we know that it will happen based on previous information that we had, and be able to somehow predict what will happen with certain amount of exactitude. So the full cycle of a project using machine learning for predictive analysis include the following steps. We have data collection. We're going to analyze that data. We're going to check statistical models to be applied. And we're going to use machine learning to keep it the training and learning of this data. We're going to validate and we're going to deploy it because we need to have this in the hands of the users in order for them to make good decisions in the future. So let's talk about a little bit about data collection and analysis. Data collection, it's in a nutshell, gathering, measuring, and storing information from various sources. So we have Excel files, we have databases, we have plain data, we have, big data that's bringing information from anywhere. That's data collection. We use this data to do the research, answer questions, test hypotheses, and of course, make informed decisions in the future. So it's crucial to have good data. In terms of the volume of the data, it all depends on the type of research that you want to do. So if you go for a simple statistical learning path, you will need less amount of data because, I don't know, a correlation, it's obviously there. You don't need a large amount of data, but the model performance will be affected. This means that what you do, you train, will be only valid for a certain specific type of data. If we go up in complexity of the algorithm, we will need more and more data. The data volume that you see on the x-axis, it grows 10 times each step, which means that to get to the, for instance, deep learning neural network, you will need hundreds, thousands of data points extra than what you need typically on the simple statistical learning. In this process, we're going to be right in the middle with the traditional machine learning approach that needs certain amount of data, but not as much as deep neural network. So this, it tries to explain that, okay, we need a large amount of data, but on the other side, we also need good quality. So it is important, being the main input, that data needs to carry relevant information with it. It has to be good information with certain amount of real information from the side. So there are ways to create synthetic data or bring information or fill with nulls, as in the machine learning said, but that information will affect the result. So your result will be directly related to the quality of the data along with the amount of data. So let's talk about statistical models. We can define statistical models as a mathematical representation of the real world, a way to describe, explain, and of course predict the behavior of a system or a process based on data. So we use that to understand what for the human being it's not on the common sense obviously there. We use mathematical approaches to understand and use that data to predict future events. We have several approaches. I'm going to just mention a few. We have the simple, I would say one of the simple one, which is the linear regression. So with the linear regression, what we try to do here is to find a function, in this case, you can see a line, that can easily describe the situation that we are seeing. So in this example, we have on one axis the amount of rainfall that you have on a typical day or a month. And on the other axis, we have the number of umbrellas being sold. So we can say, looking on this graphic, that there is a relationship between these two. If it rains, more umbrellas will be sold. So this is what the linear regression can help us, because if I only have one part of this graphic, I can predict the other one just by training and calculating that graphic line that we are seeing on red. Sometimes we do have more complex problems. we have to make decisions. We have to create a category. So it's not a numerical number that we are expecting, like in the previous one, where I put the rain and then I get the number of umbrellas. But I need a category, something saying true, false, or it's red, green, or blue. For this type of decisions, we use the decision tree. A decision tree is a tree where we have a main node, a root node on the side, and then we branch the data based on features. And every time that we are facing something, we are facing a new feature, we branch it again. With this, we are going to take different decisions on each node that will leave us with a result that will be the category to be applied. This approach, it's good for really simple data points where it's easy to calculate. There are not too many features, so I don't have to check for, I don't know, in this case, I have a question that it's not correlated with the other branch, in this case, feeling cooking. No, actually, the weather is good. Yes, okay, I will dine out. There's no relationship between whether it's good and what is in the fridge. So I can use this type of branches here. Most of the cases, what we have is a more complex scenario. So I have, in this case, I have a fruit basket with multiple fruits, and I need to know which type of fruit it is. So the question that I have to ask will affect multiple features. It's what's the color of the fruit? What's the size of the fruit? What's the smell? What's the taste? I can create multiple random decision trees, each one branching using a different approach, a different feature. They will lead me to different solutions. And after the process is done, a voting mechanism will happen, and the majority will decide what's the final answer. In this case, I have 2 apples as results for the first 2 decision trees that I have inside. And then I have a third one, which is a banana. In this case, the voting mechanism decided that the result will be classified as an apple. So that's this is an approach that is really good when you have multiple features. You have a large data set, large enough to run it, of course, and it will get you more accurate answers than a simple decision tree. There is another way to classify categories. This is the key NN, which is K near neighbor. This is an approach where giving some features, we can establish a relationship or grouping of a data set of information. So this is also mostly used in some types of machine learning. But I just want to mention this because it's somehow part of what we are going to do along with the, random forest. So machine learning, we know now what we need to check on the data collection. We know now about the statistical models. Let's talk about machine learning a little bit. The machine learning, this is the definition, but it's a statistical algorithm that can learn. This is in a nutshell what it is. We are going to grab data, and from that data, we're going to generalize results from unseen data. So I use the algorithm to train, and then I use the same training to process unseen data and get information. The key part here is that it performs the task without explicit instructions. So I don't have to teach the algorithm each step. It will be able to run some assumptions and give me a prediction. Machine learning is part of the umbrella of artificial intelligence, where we have computer vision, we have neural networks, deep learning, the LLMs are part of this. They are all under the umbrella of artificial intelligence. So, given this, we face the first decision as to what to use in this case. We have a few ways of doing it. We have three big groups under machine learning. We have supervised learning, we have unsupervised learning, and reinforcement learning. So supervised learning happens when you have labeled data. You know what is good, you know all the categories already, you know what is what. So I have an apple that it says apple, I have a banana that says banana. And I can teach the algorithm with that and use the same information that I use it for training, a different set, but the same information, to test if the algorithm is learning or not. So I need to know beforehand what are the results that I'm expecting in order to teach the algorithm how to perform on unseen data. There's another way of doing this, that it's the unsupervised learning, that in this realm, we can say that the KNN that we saw before applies to this. It's clustering based on features. Sometimes features are apparent, are really in your face, but sometimes are really hidden. So clustering allows you to compare different ways and detect differences and grouping different data points according to some features. So but it doesn't imply that you need to know the data beforehand. You will test it later, but the algorithm will not know if it's what's the category, for instance, that each one of those have, but they will know that they are different. And the third one is the reinforced learning, which is the same principle that you have before. You have your data, you introduce it to the system, but the difference here is that every time that you do an epoch, a loop, you will test that data again to validate it. And the information from that testing will retrofit again the system, and it will learn on itself based on a simple loop that it will happen inside the algorithm. Okay. So let's go to the specific proof of concept. So data collection, how we do it. So for this presentation, we couldn't use, of course, private information from clients, but in order to share it with you, we gather more than 70 projects from public databases. We are going to share it with you. Just write us an email. The data will be at the end of the presentation. This data set contains several projects from different parts of a region, and it has they have different types of buildings. So we have a really heterogenic group of projects to test. This converted to data will they will be around 300K data points around it with task resources and weather conditions and everything. So the idea of the data collection is to bring as much information, as many information as we want, as we can gather from the system. So maybe we have weather conditions of that specific project during the duration of the project. We have task information that is attached to the task name. We have the resources that we're assigning to the task. Of course, the location of the project and the category, which explains somehow which type of task is being performed. This category, we're going to stop it in a moment, but the idea is to bring everything together into a single data set. Once we have everything on a single data lake, we need to classify the information. This is one of the most costly parts. It will take a lot of effort because you got to get into the data and check if the information has some invalid data points. For instance, you have a task with a name that is 001. Okay, that task itself doesn't explain what the task is accomplishing, but you have the successors of the task that talk about the building of the structure of the columns for level 1. So we can bring that information back and put a tag to the task in order to use it later in the process. Or we have ambivalent data. For instance, coming back to we have a task called pipe, and there is no way to know if that pipe is a fire protection pipe, it's mechanical, it's sanitary. There is no way. So we need to be able to remove ambivalent data. By remove, we have two ways of doing it. One could be to remove it directly. And the other way, it could be to categorize it or add flags or tags that help understanding that situation. In this particular case, as we grab information from multiple sources, we faced the problem that tasks were not following any type of naming convention. So given that and the number of data points that we had to check, what we did is we did a small machine learning inside this machine learning project that will use the approach of vectorizing the text and finding the best match. It's not just finding some text inside the task name, but to find how far from a concept is the task name. Let me explain this. So we have a task called structural columns, which for me, human, it's quite easy to understand where it's going. If I process this with this machine learning algorithm using the vectorized strings, what I can do is I can compare it with a list of possible categories that I find that they are matching on most cases of the projects, and try to first match a category and then match a subcategory in order to apply a tag to that specific task. In this case, structural columns are 98% a match to the category structural subcategory columns. It could also be structural beams. It could also be architectural columns, but they're more likely to be that. So we use that approach to create the different categories inside our process. So what you are seeing here is the algorithm applying all the categories in our projects. This is the distribution of the different categories. What we notice in this data set, I don't know if it's true for all data sets, but it's that MEP and structural are one of the main tasks One of the hypotheses that we have is that they have really separated tasks inside a really big group. That's why they have so many. And also, they have the verification from the community or the state about if it's being placed correctly or not. So you have that part to into the classification that we're having. So I'm going to show you right now how the code looks. Again, this information will be available for you, the Jupyter Notebook. What we are doing is it's quite simple. It's solved in 20 lines of code. We are grabbing the information from the task, we are grabbing the categories, and we are splitting the model in two, and then training some information, and then gathering the prediction of that. Once we have that process done, we re-inject that information back to the original data set. So we have this. This is part of the fixing of the data. We are also doing some null checks, which is the information having something or not, because there are some tasks that have no name or they have an underscore. We remove those because there is no way to know what's happening. We are going to do some data analysis on top of that, which means to try to convert it to something that the machine can understand. For instance, previously we mentioned categories and subcategories. There's no way for me to just give the word structural to a machine and make the machine understand. So I need to create a category for that, a numeric category. So for instance, a structure, it will be category number 7. So I use the 7 as the value. And the subcategory for column will be 20. Okay, so now the code for category and subcategory will be 720 if they are structural columns, and that will be repeated on all the samples. This information I can input into the system. Another thing that I can input is, instead of putting the direct relationship between the task and the subtasks, I can just make a thesis that if a task had multiple successors, it will take more time. So I will use the information, the count of successors, and I will put it as successors. In this particular case, and we split the model into regions. So we, instead of inputting directly the weather, we did this assumption. If this is happening, all these projects are happening in between this last 10 years in the same region. And we assume that, or we are seeing the data that November is always rainy. So we, instead of putting the amount of rain that November is having, because it's consistent year by year, it's a small variation, we can just put the date, the number of the month into the system. If the rain affects somehow to the result, that will be expressed by this number, directly the number of the month. And of course, we need to figure out how to calculate the target, which is what we want to test. That information and this data set, it's coming from the difference of the target date of starting, or the target duration of the task, versus the actual duration of the task. We were lucky. Most of the information that we gathered, I already have that information. Kudos to the people doing this project, because we know now, okay, we estimate that it will take us 3 days, but actually it took us 5. Okay, so we have that information and we can use that. We also saw something really cool, which is that on all the projects, there are a few tasks that were done in less time. In this case, I have some data here. I have this one. It's being expressing that it took less time, and there are a few that are on time, and more of them are outside of these boundaries. So with this, we're going to analyze a little bit more the data. We are going to draw an histogram. This is the normal distribution, the count of tasks ordered by the amount of delay that they have. You can see that we have a really kind of smooth curve here being drawn if we average the results. This is expected because this is a normal deviation that we are having from here. We have this curve saying, okay, in the zero area, we have more tasks being done on time. We have a few tasks being done before time. That's great. And we have all this area here, whereas we are aiming to figure out how to predict tasks that took more time than expected. There is another exercise that we do here, which is just to check if there is a direct correlation. I'm just going to stop a little bit here. This is a correlation matrix. You can see that there's a diagonal here. As the square repeats itself on both sides of the diagonal, we can just ignore half of it. It's the same information. And we can check this lower half. We have the range that goes from 1 to -1. This means that if we go to red, it's direct correlation. And if it's going to blue, it's inverse correlation that we have. So what it's shown here is that we have a few clusters of, oh, there is something here. There's a correlation between the parameters. So if I up something, it will affect all the one. But with a deeper analysis, we figured out that this is not actually the correlation that we can use because it's just the result of calculation. So if I move the distance between the actual date and the actual duration and the late duration, it will affect the delay. Yeah, of course, that's how we are checking it. So this part is showing that there is a relationship between the more it takes, the more it takes. So that's a conclusion that makes no sense for us. There are a few other conclusions, but none of those were evident enough to use a simple linear regression, which led us with deciding which statistical model to use. We reject linear regression because of that. There's no simple correlation that we can use, and we use the random forest instead that allows us to have multiple features inside. So, okay, we have everything. We need just to apply it. Applying the machine learning, it's quite simple, actually. If you have the help, if the model is simple enough, in this case it is, but it involves multiple steps. So going back from the beginning, we have to graph the data, check if the data is okay, prepare the categories. Perfect, we already done that. Select the target. Okay, we need to check delay. Select the features. What we are going to use. We're going to use category, we're going to use subcategory, we're going to use the month of starting, the month of ending. We're going to use the duration of the training in order to see how it affects the delay. We're going to check that information. This is every time you're seeing a stop sign, it's a check of the information that goes back to the loop if something wrong is found. We split the model. This is really, we split the data in order to be able to test something and to train something and then test with something that the algorithm never saw before. That way we know it's okay. Then we go into the implementation. We set which algorithm are we going to use. We fit it with the training data. We check the results, and then we try to predict something using the data. So this is the whole process. I'm going to show you. I'm going to walk you through it. The Jupyter Notebook that you are seeing is bringing all the information. Is bringing the libraries. We are using Python, so it's quite simple to implement. Everything's there. We have here the list of categories that we talked before. You can change that category using whatever you are using. And we use that to inject the categories. Here we're injecting the categories into the project data. We, of course, fill the empty values. We check for anything that is null. We clean that information. And you can see that in every step, we are checking the information. We're printing what we have. Here we are predicting the categories. using the categories that we saw before, injecting it to the data. We are classifying, that way we are classifying the tasks. Again, every single step you have to check what is going on, if it makes sense or not. Here is some way of checking it visually. We are really good as humans to check things visually. We are really good at detecting patterns. So I personally prefer to have some graphics because I understand them better than just the table information. We are calculating the delays a little bit, and then we are checking here we are checking for any expressive correlation, as I mentioned before. As before, I said we found none. Printing the data, checking everything if it making sense. Here we are analyzing the delays, and then we are going to start doing the prediction. It's really quick for you to see, but what we are doing is we are preparing the data, we are splitting the data, selecting the random forest algorithm to test it, find the delay that we want to use to filter out whatever we don't want to use, and then we store the model. This model can be later used on any system in order to make the prediction back. So you train once if you want, and then you go back to the model that you trained and you implement it on any other place. So continue with the presentation. This is the result expected from the training. This is just a sample. This is not the latest and greatest. We keep improving the model a little bit. So I was finding the values are inverted here. That's why it says -1. It should be 1, but the code was operating the other way. So we are trying to get an accurate presentation, an accurate result or estimation from the data sets. So this is the result that we have. Let me just walk you through how to understand it. So we have the Y max value. That means where we cut the data to say, okay, this is detected as a delay. Everything from 1 day, it will be detected as a delay. 1 day to 120, as we saw on the histogram. What's the accuracy of the model? It will tend to 1 if it's good. If you have 1, and this is a caveat, if you have 1, something's wrong. Statistical models and machine learnings are never 100% accurate. It could be that you are using the wrong data, you did something wrong, or you are testing with data that the system already saw. So it's, hey, I know this, so I know the answer. So be aware of this. You want to tend to 1, but not quite there, okay? So you have also, we are testing one thing, which is, does this task, it's predicted to have a delay or not? This is a binary question. So we have the true. Oh, this task will have a delay. It's expressed with the number 0 on the true, false, positives. That means that, okay, it will predict that this task will have a delay. But there's another way to think about the same question. How many times will the algorithm detect a task that has no delay as delayed? So it's a true positive, false positive that we want to check. You want to have some weighted or macro accuracy around 1 again. That's a healthy model. And you also want to have a really F1 score between the two options, the false positive and the true positive and the true false. That matches the same thing. So you want to be able to predict when it will have a delay and when it's not. Both things are important here. So we are getting to the end of the presentation. I want to show you, okay, how we use this. Okay, because so far what we did is collected the data, we created the data, we injected more information to be relevant to the data, we trained the model, we use it on the test, but okay, what I do with this? So the implementation that we will share with you, it's capable of inputting a Primavera project that if the Primavera project, it's more complex than a Microsoft project because it can be converted into separate data sets. So you have your resources, you have your schedules, you have the task. Everything is on a different spreadsheet. So we have to remerge that when you export it. That's the first step. We're gonna import, process, merge the data. We're gonna predict the categories, and part, this is the part that it will change the most on you, because it depends the categories and how you present it. It depends on your projects. So it's important that you know how your naming conventions are in order to hard code some parts or make predictions more accurate for that part. Then, once we have that, we detect the delays. There is another part that I didn't show here in the presentation, but the same code has it, is predict the amount of delay. So we have two things that we're going to present as a result, which is this task uh, estimated to be delayed? And also, how's the likelihood of this being delayed by this amount of days, which is something that you want to know, how much it will delay. This result, it's going to be raw. You need to format it. The best way of we found it's to make it more compatible with all the situations is to format it to a CSV file with a number ID, a task, the ID of the task from the original data set, from the original project, the task name, starting date, end date, duration. That's it. It's quite simple and can be imported into any scheduling program. So this is how the result looks like. There is no interface for this. This is code. But when we start the process, we thought about creating an interface or something, but the people working with this schedules, they were really familiar with the scheduling tools. So we thought, oh, let's just give something that they can use directly, no interfaces. So we are doing here is we are mapping the information that's coming from our prediction. It will be imported. And the cool thing is that you can compare the original schedule with the new schedule that we are proposing and make some graphics with that will help you communicate. Hey, this task, it can be delayed in the future. Have that in mind. So it's just about that. It's to uh, putting a flag or just a heads up to the people on the field that, hey, this task can be delayed. That's it. What we propose, if someone is interested in this, is to train your model locally with your data. Once you have it, it's a small file that you need to use. It's really small in terms of the hardware requirements. You pack it, you deploy it on the cloud. It could be serverless, it could be a computer, it could be your computer with an open network connection. And of course, create an access through the internet. We thought about just a drag and drop. You drop your file and you receive a corrected schedule from the system. That could be an implementation. You can connect directly, like a data source, from the web directly to your systems. That could be also one way of implementing this. Here's what I think it's the most important part, along with with the code, of course, about this is what we learn about this implementation. So we started this for a client. It's not the same project, it's something else, but the approach is similar in terms of, oh, I need to ingest this amount of data that I already have and do something, a decision with the same data for the future projects. So the first learned lesson is, oh my God, yeah, don't trust your data just because. Go into the data, check. People are lazy. They are not going to be filling all the information as you want. It will take them, they will do some shortcuts. They will use some acronyms that you have no way to know what it is. So check your data. And also, once you check it, you're sure the result of this is just a suggestion about what you do. It's not written on stone. So it could be something wrong. It's a good way of do a heads up, but it's not a good way to handle the whole process of the construction. Okay, so confirm your data. Remember, garbage in, garbage out. Suspect from perfect predictions. So at the beginning of the process, we started really good. We went to perfect. Oh, what is that? How we can go to perfect with a statistical model? So on our situation, and we pick it up this in time, but we split the model into two parts. This is the training, this is the test, and somehow it leaked the information, and we overfit the model. What this means? You can see that here I have three different ways of predicting the data. The graphic that you're seeing, the line, is the prediction of something. So I can have an underfit, which is that the predicted value will not fit the information that I have to test. It will not fit. This is wrong, but this is easy to spot because your information is not going to be good. The predictions are not going to be good. The other way is that you have an overfit. The predictions are to the point with the data that you have. This will never happen. If it happens, it means that something went wrong. You cannot have 100% accuracy on a statistical model. You have 95%. 80 will be a good number. So everything above 70, I would say, hey, kudos on you. And when you test that information with new information, you will see that, oh, the prediction is quite off. What you want is to have a nice, smooth curve that will predict most of the cases with a really good accuracy. Okay, so this is what you have to look for. Another learned lessons is that nobody knows your business better than you. So have that in mind. It's kind of difficult to buy something out of the shelf in terms of this type of things. You have different ways of doing something that the next company. It will be different. So have in mind that even if you buy something out of the shelf or vanilla, ask the people creating the software how you can really implement some custom things that match your data. There is no company using the same conventions, so the same information is not always the same categories that you think are universal are not. So use your knowledge to teach the people doing the work what you want, and also analyze the results if it's something that you want actually need in your company. Those two ends of the process need to be really curated by you. You need to put a lot of input in this. And okay, hardware requirements. This is a hard question in terms of it's not soft. For this approach, any computer can work. If it's kind of modern computer, not Pentium 3, but it will be able to run this. Everything here can be also run on the cloud. Google Cloud, it's a great tool to do this mockups and to do the products. You can train on that. Once you have the training, you download it and you implement it on the cloud. And with this, sorry, we plan ourselves. What are the next steps? So actually, the next step for us was just to do this webinar. We wanted to share a journey with you. We wanted to help somehow other people help us on this, and we wanted to share. Sharing is caring, so we like to help the community with anything that we have. And for us, there's no product in the future. There's no pitch sale here for us on you. But if you need to create something, you want to create something, again, my data will be at the end of the presentation. You can just ask us. We can give you the data set and the code. But if you have any ideas and you want to build something cool, ring us. We are more than happy to help you with any solution that you want. And finally, yeah, questions. I don't know if anybody has some questions. Okay, I have something on the private channel. So what's the minimum amount of data? That's tricky. It depends on the quality of your data. For this project, I would say that we went to 70 projects as we established before, but I think that if you have more than 50 projects, 100 projects will be ideal. That will be ideal. With that, you can get a few good results. Again, that will not make any sacrifice into your requirements on the hardware side. It will be enough. What you have already for the 70 will be the same for 100. I don't know how many companies can have more than 100 project schedules being updated, ready to use. But if you have those, you are a great candidate for this approach. So yeah, that's the answer. Okay. Um, that's I think. Oh yeah, neural networks. I wanted to mention that we didn't go with the neural networks uh, type of approach, which is you have an input, something hidden in between, and then an output, because we didn't have enough data, and the data was not that difficult to understand for the machine learning. So we just went with a simple random forest for this. But it could be a good approach if you have multiple sources of information. And again, the information, the correlation, it's not evident. So, okay, perfect. Thank you. Anything on the private again? No. Cool. So, here is my information. Feel free to reach me or the company. You can go to Evers to check it out. And it's my LinkedIn, my phone number. Feel free to reach us with any questions, and we are going to be more than happy to help you. Again, thank you all.